Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Michel Talleyrand is one of the world's great probabilists, and we're very honored to have him giving this talk today. He's had a big influence on our field, especially through his work on concentration of measure phenomena, and more recently his work on spin glasses. His book on the latter topic, as well as his book with Michel Ledoux on probability in Banach spaces, are classic texts that are referred to by many people in our field. And today, his talk is going to be entitled, Are Many Small Sets Explicitly Small?
Thank you very much. About 20 years ago, I discovered a series...
You need volume on the mic.
The mic.
Can you flip it closer?
Closer. About 20 years ago, I discovered a series of problems which I think are potentially important and which at least are fascinating. And of course, nobody cared about these problems. And I'm very grateful for the organizer to give me a chance to change this. So what I'm going to do is I'm going to explain these problems in their proper context and why I believe it would be nice to solve them. So what this is about? Well, the general philosophy is as follows. In a space with many dimensions, if you take a large set, then most of the points of the entire space are close to the set. So that's the idea of concentration of measure. Now you see in that statement there are two words which are between quotes. It is most points are close to. And a set is large. So set is large, then there is no much room about that. We are going to have a probability measure on the space, and the set will be large if it's of probability, say, at least 1/2. Now, most of the points are the results that are classical in concentration of measures. They deal with saying most of the points mean the set of points, the exceptional set of points is of small measure. And here, now, in this talk, I will suggest some other ways to look at that. And the points are close to A. Now, close to A here, this is wide open to your imagination. How do you define a point being close to a set? And then there is a potential there to discover new things. And actually, that's a line in which I was successful some time ago by finding some new notion of how to measure the distance of a point to a set. And now I'm going to suggest new ideas, except the problem is I cannot prove anything about it. So the goal is to obtain statement independent of dimension. Now, when one of the problems of computer science and many other areas is that it's difficult to study sets in many dimensions. And the best way around that is to find statements which don't depend on how many dimensions you have. So the problem is somehow completely pushed aside. Now, the main theme of the talk is that apparently there are still mysteries about the structure of large sets in many dimensions. So it's a kind of either the conjecture I'm going to propose have a positive solution, and then it means that there is some kind of general structure for this set that we do not see yet, or these conjectures are wrong. And if they are wrong, it means there are new patterns, new configurations to make sets of large dimension that we didn't discover yet. So in any case, if we solve this problem, we may learn something which is important. Now you're going to tell me, what does this have to do with computer science? Well, what do large sets in many dimensions have to do with computer science? Well, they are not going to help you to maximize tensors over, probably they are not going to help you to maximize tensors over unit vectors. Okay, but in the long range, they may help you to look in the right direction. So to put it in a positive way, you cannot really prove that this has nothing to do with computer science. Okay, so the basic space. So the basic space is a two-point space and its product. Now the two-point space, that's not a high-dimensional space, but when I take many product of it, it becomes high-dimensional space. So I take only a finite product. So my basic space is the set 0, 1 to the s. And you will use the notation, if you can remember it, little n is a cardinality of s. Now I need to set the terminology right, because it's very convenient when you work with the space 0, 1 to the s to identify its point with the subset of s. So a point in 0, 1 to the s is a subset of s. Now I'm going also to study the subsets of 0, 1 to the s, and these I give them a different name. I call them class. So the reason for that, if I use the word class, it's the class of subset of S. And the notation classes, I will denote them by A, B, C, sometimes F. And subset of S, I will denote them by I, G, and Y. Y when it's a random subset, as I'm going to explain now. So basic probability on the two-point set, well, then you consider a small parameter P, and you put simply the weight 1 at P and the weight 0 at 1 minus P, and you consider the product measure, which I will call throughout the talk, I will call mu sub P. So if you like to think what is a random set for mu sub P, is simply a set where every point of S you decide by flipping a coin whether it belongs to the set or not, but the coin has only probability P to put the point in the set. Okay. Now, some more definitions. A class of set is called an up class if it has the following property. Whenever I take a set belonging to the class and I take a larger set, it also belongs to the class. And the down class is the opposite. Whenever I take a set in the class and I take a smaller set, it also belongs to the class. Now, why do I consider these? Well, because up classes and down classes are somewhat simpler than general classes, and there is little hope to understand general classes if I don't understand up classes and down classes. So that's a natural place to start. Now, obvious observation, if I consider an up class, then its complement is a down class. Now, here is the most important example of down class, the Hamming ball. So B is the class of subset of S, so that their cardinality is at most a given number K. And simple observation, now for which values of K is B going to be of measure about 1/2 for mu P? Then of course when K is about n times P, where n, I remind you, is the cardinality of S. Now why this set B plays an important role? It's easy to understand. When you are studying a problem like consider a subset of, consider a class of set, and let us assume it's of measure at least 1/2 for mu P, and let us consider how far are the elements that are far from that class. Well, somehow the class B, you understand that it's going to be extremal because it's it's arranged, it's packed as nicely as it can be. So this, whenever you think that a statement could be true, it's very fruitful to try to test it on the class B. And if it's true on the class B, well, it has happened quite often in the past that it was true for much more general classes. So, another object I'm going to consider is now the following. Given a subset I of S, I define the set H sub I, which is simply consists of the subset of S that contain I. So this is an up class, of course. If I have a set which contain I and I enlarge it, it still contain I. And the measure of that that set, H sub I, is P to the cardinality of I, because each time I fix one, say I fix one coordinate equal to 1, it gives me a factor P. Now, why this strange name H sub I? Because you have to think that as being a kind of half space. So, in any case, the set H sub I, they are also very canonical in their own way. They are as simple up class as you can define. And they're going to play a very important role in what I'm going to explain now. Okay. Now, here is the most important definition. Now, I consider an integer q and class A. And I define the class AQ as follows. So this consists of the subset G of S that cannot be covered by Q elements of A. Whenever I take Q sets in A, they do not cover J. So obviously that's an up class. If a set cannot be covered by Q element of A, then any larger set cannot be covered either by Q element of A. And the idea is that the point in AQ, they are sort of far from A. Well, they are far from A. They are said they are so far from A that I cannot reach them using Q sets in A. Now, the main conjecture is that if Q, there exists a number Q, which is a constant large enough. Now, here I put some room, but probably Q equal 10 would be just fine, which has the property that whenever A is not small, then the class AQ is very small. So that exactly fits in the framework that I mentioned on the first page. I have a set A which is not small, then think of AQ as consisting of sets very far from A, then AQ is very small. So that's going to be the main conjecture. But the point is what's going to be the meaning of very small. Now, the meaning of very small will not be that this is very small in measure, because there is a trivial example that it's interesting to consider is when the class A consists of the empty set only. Then what can you cover by taking Q copies of the empty set? You cannot cover anything. So when A consists of the empty set, then AQ is just the complement of set. All non-empty sets cannot be covered by Q copies of the empty set. So in that case, the measure of AQ is just 1 minus the measure of A, because AQ is the complement of A. And okay, and then however large you take Q, this is not going to be small. 1 minus mu P of A is 1 minus P to the n, depending on the choice of P and n. This is whatever you want. Okay, so the notion that AQ is going to be very small is something else that I'm going to define now. So here is the definition. Is well, you know, the funny part is that I didn't use my computer because I saw there would be formatting problems with using the computer. Now I see the formatting problem, they're here. But okay, so a class of set is P small if I can find a family of subset of S which has the following two properties. First, C is contained in the union of the set H sub I for I in my family. And number 2, the sum of the measures of the F sub I is less than 1/2. So here I put 1/2. The value 1/2 is not important. You can put 1/3 or 1/4. So as long as you don't put 1, this is any number will give you basically the same theory. Now the condition 1, if recalling the definition of F sub I, it simply means that whenever I take a set in C, then I can find a set I in my family, script I, which is contained in that set. So what means such a definition? It means that, you see, it's difficult to tell how large a set is if you are in many dimensions. Here, when a set is P small, there is something special happens. I can say I have somehow concrete witnesses that the set is small. The set H sub I are concrete witnesses because my set C, it's contained in a union of this very geometrically simple half space H sub I with the property that the sum of their measure, not the measure of their union, but the sum of their measure is small. So it's a very strong property and it's very explicit. It should appeal to people in computer science who like to have, you have to have an objective checkable criteria that a set is small, and somehow here is one very, very strong. Now, simple observation is about P small set. When you make P smaller, then you get more P small sets because the quantity here decreases with P, simply. Now, what does it mean that a set is P small? Well, later on, I'm going to prove the following, which is very simple when you look at it in the proper way. It's if you give me any value of delta and any value of P, then I can find upclasses for which mu P of A is as small as you wish, but A is not delta small. So it's really a notion, this is being small for mu P and being delta small. This is something, there are different notions. Of course, it is being, if a set is P small, then it is of measure mu P less than 1/2, of course, because it's contained in the union of the H sub I, which itself is of measure less than 1/2. So if a set is P small, it is of small measure for mu P, but the converse is completely wrong. Okay, now I said whenever you want to discover something about upclasses, you have to look at this basic example, this Hamming ball, the set where the cardinality, the set with cardinality less than k. So let us prove a very simple fact so that you can see how it works. I'm telling you, if I choose P in such a way that mu P of B is at least 9/10, and if I take Q, say, equal 100, then the class BQ is P small. I'm going to prove that. Now, Q equal 100, there's no attempt to be sharp. Probably Q equal 3 works. So, what is BQ? BQ consists of the sets that cannot be covered by Q elements in B. Now, elements in B, they have cardinality less than K. So, in order not to be able to be covered by Q sets of cardinality K, then the set must have a cardinality Q times K plus 1. So BQ simply consists of the subset of S which have a cardinality at least small s, by definition, Q times K plus 1. Completely trivial. Now, if a set G belongs to BQ, then it has a cardinality bigger than QK plus 1. So in particular, it contains a subset which has cardinality exactly S, which is QK plus 1. So here I rewrite the definition of H sub I. H sub I, they are the subset of S that contain I. And what I have proved here is BQ is contained in the union of the H sub I, where the union is taken over all the set of cardinality S. And what is the sum of the mu p of H sub I for this class? Well, they all have the same measure, which is p to the s, because the measure of H sub I is p to the cardinality of I, and here cardinality of I is s. So each of them has measure p to the s, and there are n choose s of them. So now I'm going to it's becoming short-sighted, or that should, okay. It is. Now, if mu p of b is bigger than 9/10, I'm going to show you that the sum of the mu p of H sub I is less than 1/2. Now, of course, something like that has to be very simple, and it is, but so first thing you have to check, you have to look at separately to the case k equals 0. Because k equals 0, that's the case where B consists only of the empty set. Then S is qk plus 1, which is 1. Now, n choose S, S is 1, so that's n. P to the S is P. So, in that case, this quantity is NP. So, the statement just means that if mu P of B, which is 1 minus P to the N, is bigger than 9/10, then NP is bigger than 1/2. Now, that's true. So it's completely obvious to check the case k equals 0. Now let us check the case k bigger than 1. Now k is bigger than 1, it takes 3 lines, but it's very interesting to see how it works. So n choose S, you use the half-trivial bound, which say that n choose S is less than 3n over S. Probably here you can put E, but let's put 3n over S to the S, P to the S. So now that's nice, you have 2 power S, so you put them together, 3np over qk plus 1 to the S. Here denominator is S, I just replace by its value, which is qk plus 1. Now, when mu p of b is bigger than 9/10, it means that basically k is bigger than np. So in the denominator here, since q is 100, 3np over q is 100 and k is basically np, so this is surely less than 1/2. So this fraction is less than 1/2, and then you raise it to the power s, which is rather large. So this is less than 1/2, and in fact it's also much less than 1/2 that you see. So conclusion of this computation, well, that proves the proposition. Proves the proposition here. If for the class B, which we believe is really the test, the fundamental test case, and for the class B, if it is of measure at least 9/10, then the class BQ is P small. So that's very easy to check for the class P, and now the question is that going to be true for so, main conjecture, if Q is large enough, so there exists a Q independent of anything, which has the property, then for any P, if I take a down class A, which is of measure close enough to 1, then the class AQ is P small. Okay, so now I stated that conjecture this way because it involves only very simple object. Now I'm going later to relate it to other questions. Now it's okay. It's a problem. You're a little bit cornered with that because the basic objects are so just that, so basic and so simple. So what do we do? What do you do with it? So it's a nasty problem. Actually, I have to confess something. You know, every time I have an idea about that problem, I shave my head. Huh? You know what you. I offer a nominal price for solving the main conjecture, and of course the price is nothing. But I promise you, there is a very good recommendation letter going with the price. Now, when I mentioned this price to Noga Alon, he made a very nice comment. There are easier ways to make money. That's what he said. Now, here there is something important I have to say. You see, keep in mind, the $1,000, they are just for bringing the solution to me. Huh? You do not need to find it yourself. Now, it is if you buy it from somebody else for $500 and you bring it to me, you get the whole 1,000. I don't ask anything. I just want to know. Okay. So that finishes the first part of the talk. Now, this main conjecture, it has links with analysis and geometry, with probability, and with combinatorics. So what I'm going to do in the second part of the talk, I'm going to explain the link with analysis, geometry, and probability. Now, of course, I will not be able to help to talk about my favorite obsessions. Now, if some of the things in that part of the talk you don't like them, it's not so important, because in the third part of the talk there'll be a fresh start. I will discuss the combinatorics, and I will discuss the thought I had about the main conjecture itself. Now, of course, I could not solve it, but I tried to reformulate it, and it's very interesting what happens when you try to reformulate it, because in one word, is that when you cannot solve a conjecture, well, the best way is to look for a stronger conjecture that you can disprove, and at least you can learn something. But when you cannot disprove the stronger conjecture, what do? You find a still stronger conjecture. And then when you iterate many times, you get some very interesting things that I will explain in the third part. They cannot possibly be true, but if they are true, then that would be extraordinary. So, now, here let me talk about different things. Now, about convexity. Now, why? You see, I didn't get up one morning and came up with this main conjecture. No, it's a more complicated story. It comes from other problems which are sort of more natural to raise at the first step. And here is one. You consider a subset in Euclidean space, and you want to construct its convex hull. Now, how many operations do you need to reach the convex hull? So there you use Cath-Theodori theorem. If you have a point in the convex hull of a set in dimension n, then it's in the convex hull of a subset of cardinality n plus 1. So somehow, every point in the convex hull, you can reach it by making n additions and n multiplications. Now, that's a number that's growing with n. Huh? That's not the right question. So the multiplication by a number is not important. Really, the most important thing is how many additions do you need. I just explained you need about n additions. Now, suppose that you ask the question in a different way. Now, you take a large set in Rn, and how many operations do you need to create convexity? What does it mean to create convexity? What does it mean a large set? Okay. Now, you take a probability measure on R to the n. The standard, the canonical Gaussian measure, the one that makes all the coordinate independent standard Gaussian. And say that a set is large if it has measure 1 minus, 99%. Now, in order to remove the problems related to the multiplication by a number, I will consider a only balanced set. So a balanced set is a set which, whenever I take a point in a set and I multiply by a scalar with absolute value less than 1, then I'm still in the set. So a balanced set that looks, well, supposed to be symmetric here. It looks something like that. So when you look at a balanced set, you have already made the multiplication by a scalar, and to construct the convex hull, you need only to think about additions. So here is a very beautiful conjecture. Now, conjecture is as follows. There exists an epsilon, say epsilon equal 100, and an integer q, say q equal 100, so that whenever I take a balanced subset in R to the n, which is large, it has measure 99%, and then I take the Minkowski sum of itself q times d plus d plus d, which means I consider all the sum x1 plus xq, where x1 belongs to q, and so on. Now, inside that sum, then I can find a convex set which is large, in the sense it's of measure at least 1/2. So this statement, if it's true, it would mean that, contrary to the first impression you might have, to create convexity starting from a large set, you don't need a number of operations that grows with the dimension of the space, but no, it would be possible to achieve that with a number of operations which is absolutely independent of the dimension. Now, I think that would be very, very beautiful if it were true. Now, it's a nice problem. Now, I spent some time studying that, and the only thing I know is the case q equal 2 doesn't work. It absolutely doesn't work. There are obstructions, but I don't know about the case q equal 3. Now, what's the difficulty in that problem? Well, the difficulty is, assuming it is true, then you have to find a method to construct that convex set. And assuming it's not true, then you have to find obstructions for which they're preventing that they're.
Do you require C to contain D?
What is A? I start with D.
Yeah, but you don't require C to contain D. It's not like finding the.
No. Oh, no. Yeah, it's somehow, you see, when I say it creates convexity, you don't create the whole convex hull. You just create a part which is big enough, which has measure 1/2, where you already have convexity. You create enough convexity, not the entire convex hull. That's what it is. Now, of course, it's difficult to explain why this is such a nice problem. The best way to understand that is try yourself to take a set in n-dimensional space and compute that sum, and you'll see whatever you start from, it becomes absolutely huge. Now, the main conjecture is a kind of discretized version of the convexity conjecture. The way you have to say, okay, the main conjecture deals with a down class, and the convexity conjecture deals with a balanced set. And you have to think that AQ is really discrete analog of the complement of D plus D plus D. You see, DQ are the sets that cannot be covered by Q sets in A, and being covered, so it's a kind of sum you are making. So you can think that's one way you can discover the main conjecture is by studying that. Now I'm going to talk about stochastic processes. Now that's a very, very scary word, but somehow the way I'm not really a probabilist. You know, I started in functional analysis, so for me a stochastic process is some very basic object, is simply a collection of random variables. That's what a stochastic process. And it's indexed by, it's indexed by a set T. The reason I still call the index T, because, of course, when you use stochastic process to model something that depends on time, T is the time. But here, you're going to see the...
Can I ask a question about the previous...
Yeah, sure, please.
Why was the P minus, the P measure that was...
mu P, what does it have to do with Gaussian measure?
Or P
no.
smallness. Why was that the particular notion of smallness that was right?
Okay, now I'm not sure. Okay, let us stay at the superficial level. Here you start with a set which is not small for mu P, and here you start, which has measured 99% for mu P, and here you start with a set which has 99% measure for the Gaussian measure. Okay, that's it.
No, but why? Okay, here you construct a convex set, and in the case of the main conjecture, you require that the complement of a to the q...
No, a to the q is, you have to think a to the q corresponds to the complement of the sum. It's already, the complement is already built in a to the q.
Yes, so is there, and you require this to be p small?
Yes,
so
I would like it to be p small. Now I'm going to explain something here. I'm going to make more connections in 5 minutes about the two. Huh? Yes, this is the first set of connection. Okay. So the problem I've spent the most time in my life to study the following is really you have a family of random variable and you try to estimate the supremum of this family. So in particular, you try to estimate the expected value of the supremum. And I was foolish enough to try to look at some very general situation and try to understand them completely, in the sense in trying to obtain complete classification results, which is a very ambitious program. See, somehow my philosophy is that it's very interesting to study such and such problem with a lot of structure, but you have some basic situation in mathematics that really should be understood, because they're going to come up again and again, and those are of that type, even if it's not always obvious at the beginning. So first, I'm going to talk about Gaussian processes. So, Gaussian processes. Now, if I take a point in Euclidean space, then the dot product map, the maps that sends x to t dot product with x, it defines a random variable. So it's a map defined on R to the n. And if R to the n, you think it's provided with a canonical Gaussian measure, this map is a random variable, and I call it x up t. Now, I want to consider a family of these. Now, each of these random variables is indexed by a point in R to the n. So to consider a family of these, I simply consider a subset of Euclidean space. So to me, a Gaussian process, that's simply a subspace of R to the n. So I give you a subspace of R to the n, and the problem is to understand what is the size of the supremum of this variable x sub t when t belongs to the set. And in particular, trying to understand what's the expectation of that quantity. Now, when you want to bound the supremum of a family of random variables, there is exactly one tool. Huh? There's really one thing. You have to find bound for that the probability of the supremum is bigger than a certain number u. And the main tool to do that is the union bound. The union bound, which trivially say that the probability that the sup is bigger than u is less than the sum of the probability that the individual variables are bigger than u. Now, union bound is very useful, but it's a little bit crude, because it's very efficient if your family of random variables, they look more or less like if they are independent, but if they are almost all the same, this is very inefficient because you are counting, obviously, if they are exactly the same, you are counting same probability too many times. So if you have a situation like that, here, this is your family of random variable, and you want to bound the probability that the supremum is bigger than you. You're not going to use the union bound directly. You're going to do something more clever. You are going to choose a specific point there, and you are going to say that, okay, if the supremum of the xt is bigger than u, then either it's xt0, which is bigger than u over 2, or xt minus xt0 is bigger than u over 2. And what you gain when you do that is here you have only one term here. And here you can use the union bound, but what you gain is for each of them t is close to t0. Oh, so t is close to t0, so these numbers here are very much smaller than those. You have the same quantity of the same family of it's indexed by the same set, but the numbers are very much smaller. Now, this simple idea, you have to elaborate a little bit on that. Now, when you get more complicated situation where that's your index set, what do you do with that? Well, you try to regroup the point, and and then you invent something which is called chaining, and which is just really organizing what properly this idea to decompose in several steps. It's a very powerful idea, and by working on that, you can succeed in understanding very well the supremum of Gaussian process. And the result is the following: there exists a universal constant. So I say you can compute the supremum of the Gaussian process as a function of the geometry of the metric space TD. Now, I recall you that the Gaussian process is indexed by a subset of Euclidean space. Now, the subset of Euclidean space provided with the Euclidean distance, that's a metric space. So there is a quantity which depends only on this metric structure, which is equivalent to the size of the Gaussian process on T. So you have both way inequalities. It's say the expected value of the supremum of the Gaussian process is of the same order as this quantity here, which I denote gamma 2 of TD. Now, it's not important that I explain precisely what is the quantity gamma 2 TD. In one sentence, it measures the maximal size of certain trees which are contained in the metric space. Now, it's important to understand what a result like that does. You see, a result like that does not do any magic. There are some concrete Gaussian processes for which I do not know how to estimate the supremum, because the combinatorics are complicated, and complicated combinatorics, you have to solve them directly. There is no magic wand that will ever remove them. But what these results say, that if you want to compute the expected value of the Gaussian process, the sup of the Gaussian process, there is no other way than understanding this functional gamma 2 for your specific example. You have to understand the combinatorics in that way. There's no point to look elsewhere. Maybe you can do it, maybe you cannot do it, but that's the way it will be done. And the reason I cannot do it in this practical example, there are classes of functions which some condition on the partial derivative, and it's very messy, and it's hard to do. Okay, so a statement like that, it directs your research. You know, it tells you how you can solve the problem and how you cannot solve it. So, and this kind of ideas has used in computer science. For example, the dimension reducing principle, like the Johnson-Linenstrauss lemma, and deeper things that have been done recently, they all rely on that. You know, and the reward when you study try to look at basic objects is that I say they keep coming now. Probably in that building here a few days ago there was a conference by Yuval Perez who solved, with other people, who solved a long-standing problem about cover time on graphs, and there is this functional here comes in. Okay, now a non-trivial corollary of a non-trivial corollary of what I just explained is as follows. Now, when I say it's a non-trivial corollary, it means it takes about 1 page to prove it, but you have to understand the mechanics, what is really this functional gamma 2. So when I give you the statement, you are not going to find see any relationship. Huh? Just take my word, this is a non-trivial corollary. So it says the following. It says, look at the set where the supremum of the Gaussian process is exceptionally large, means it's 100 times its expectation. Look at this set here. So, now, this set has a very interesting property. It's contained in a union of half space. Now, this time they are half space in the geometric sense. You have a hyperplane, and that's all what is one side of the hyperplane, such that the sum of the measures of the half space is less than 1/2. Okay, so this exceptional set where the supremum of the Gaussian process is abnormally large, not only it is of small measure, but it has these very simple geometric concrete witnesses telling me that it's of small measure. It's contained in this union of half space, the sum of which the measure are less than 1/2. It sounds very much like the main conjecture. And that's how, of course, that's... Okay, one thing I want to mention, another corollary which you will probably like. It's a geometric fact, you see, purely geometric fact. There is another universal constant with the following property. Whenever you start with a convex balanced subset of Euclidean space which has Gaussian measure at least 1/2, then you can do the following. You can blow it up, so that's the original set. You blow it up by this factor L, then the complement of the blown up is small in the sense that it is contained in a union of half spaces with the sum of their measure is less than 1/2. So that's a purely geometric statement. Now you need to know something about Gaussian processes to prove that. Okay, now we saw that, we saw these. Let me reformulate the convexity conjecture after doing that. Now, I just explained that when you whenever you have a convex set, if you blow it up enough, then the complement is contained in the union of half spaces. Now, so you can formulate the convexity conjecture in the following way. There exists an epsilon positive and an integer q, so that whenever you start with a balanced subset of Rn, which is of measure, say, 99%, then you can find half spaces so that the sum of the measure of half space is 1/2, and the complement of d plus d plus d is contained in this union of half spaces. Now, this is equivalent to the convexity conjecture by the previous result. If you can find a large convex set in d plus d plus d, you just blow it again by this constant factor and the complement of it, and it's contained in these half spaces. So that's a very nice way to formulate the convexity conjecture. Now, it could be misleading, because assuming when you formulate like that, you might want to think that the proper way to solve it is to construct these half spaces. I don't know if that's the proper way. Maybe it's not the proper way at all, but I formulate it that way because it makes it obvious, a parallel with the main conjecture. Now, the main conjecture, you wanted the set AQ, so the set AQ is really correspond to that, d plus d, the complement of d plus d plus d, it's contained in the union of set H sub I so that the sum of their measure is less than 1/2. Okay, so that's really, really the first time I thought of the main conjecture was really as a discrete analog of the convexity conjecture. Okay, enough about Gaussian processes. Now I'm going to talk to you about other type of processes. Random selector processes on set. Now, here's the problem. I will denote by y. Now I come back to the original setting, the measure mu p on 0, 1 to the s. So I denote by y the random subset for this measure. Just means, as I explained, every point I decide at random independently whether it's in the subset or not. Now consider a class of subset. Now what I do is for every set in the class, I look at the cardinality of the intersection of I and the random set. Now, if I look just at one of these, then I can expect that this should be about p times the cardinality of I. But I take the supremum over all I, and then I look at the expectation of that. And I would like to understand this quantity as a function of f. The idea is, of course, if f is large, then that has a tendency to be larger. For example, if S consists of all the set of cardinality less than k, then provided y is large enough, I will find this is equal to k. So let us think of the following game. You see, I give you a class F, and I ask you, please give me a good reason for which EP of F should not be too large. So you're going to think 1 minute, and then you'll make the following observation. You're going to say, oh, of course, the cardinality of I intersection and Y, that's at most the cardinality of I. So this is less than the cardinality of I. So this is less than the supremum of the cardinality of I. And that's non-random. There is no expectation here. So I have found the trivial bound. EP of F is less than the supremum of the cardinality of I for I over my class. That's a trivial bound. Now, okay, let me ask you now, please find a little bit more subtle reason why EP of F shouldn't be too large. So you go back to your office and you try to use the union bound. And you try to use the union bound, it takes 1 page, and you find the following result. You assume that there exists a number m bigger than 1 with the following relation: the sum over f of p cardinality of g over m to the m is less than 1. Now this is not very intuitive, but you understand this is a smallness condition, because if you look at the sets in the class F of a given cardinality, then there cannot be too many of them. But really, it's this 1-page computation from the union bound. You see, if this occurs, then EP of F has to be less than 100 times m. It's a simple obstruction. Okay, so now we have 2 different reasons why EP of F cannot be too large. We have this one, and we have the previous one that I just copy here, cardinality obstruction. And now I'm asking you the third question. Now, well, you gave me 2 really different reasons why EP of F cannot be large. Can you come up with a third reason, with a new reason why it couldn't be too large? Now, there is a basic difficulty here is that different types of behavior can mix. So here is how it goes. Now, if you have 2 classes, let me define their sum. Now, maybe that's not a very good notation, but the sum F1 plus F2 is just a union of one set in the first class and one set in the second class. Huh? Now, the cardinality of I1 union I2 intersected with Y, this is less than the cardinality of IY intersected with Y plus cardinality of I2 intersected with Y. Now, if I take the supremum for I1 in F1 and I2 in F2, and I take expectation in that, then I get the trivial relation that EP of F1 plus F2 is less than EP of F1 plus EP of F2. Now, another trivial observation is, let me say that if when I have two classes F and G, that G dominates F if every time I take a set in F, it is a subset of a set in G. Huh? Now, then, if you think 1 second, you see that you have the relation that EP of F is less than EP of G. You just write the definition and you use the fact that this can be replaced by the supremum here in G instead of in F, because the set here in F is a subset of a larger set in G. So if you combine these two things, you see that when you have three classes, F, F1, and F2, so that F1 plus F2 dominates F, then EP of F is less than EP of F1 plus EP of F2. And the interesting situation here is if you can bound EP of F1 and EP of F2 for different reasons. Say you can bound EP of F1 by the cardinality bound, and you can bound EP of F2 by the union bound. Then that gives you a bound for EP of F. So to put things in another way, there is a subtle way you can tell me that I have an obstacle for EP of F to be large, is because F is dominated by a class F1 plus F2, so that EP of F1 cannot be large by the cardinality bound, and EP of F2 cannot be large by the union bound. It's a mixture of two behaviors. Okay, so now after you observe that, you say, okay, is there still another way? Is there possibly another reason why EP of F couldn't be large? And I conjecture it's not true. So I cannot prove it, but I conjecture the following. So I conjecture the following. There exists a universal constant which has the following property. Suppose you consider any class of F, and you suppose that EP of F is bigger than 1. Now, that's really mild restriction. It's simply to avoid trivial situation where you consider a class of set consisting only of one set which has only one point, and trivial situation like that, where the conjecture is not true. Now, is it true that you can find another class, G, which has the following two properties? Now, first, every time I give you a set in F, it is nearly contained in a set in G. It's nearly contained in the sense that the difference I minus J is less than Lm. And the second condition is that if I apply the union bound to the class G, then it would say that EP of G is of order M. So another way to put that, it would say that any class of set is a small perturbation of a class G for which the true value of EP of G is given by the union bound. Now, its reason for which it's a very difficult problem is that the way it goes, you see, I give you F and you have to find the class G, and the class G is not contained in F. It's somewhere outside. You have to construct it. And the elements of G, they are not painted in red to help you find them. You have to find some way to construct them. Now, amazingly, as it sounds, there are situations where problem of this nature could be solved, that exactly this type of construction could be done. But here I could not do it. I could not do it, but at least I can come up with this conjecture, and if this conjecture has a positive answer, which I hope it does, then you can say, okay, I completely understand selector processes on set, if that problem. So that would really completely clean the problem. But this is not really the problem. The problem, there are more general classes of processes you would like to understand. And now here is the more general class of now I'm going to define another family of random variables. Now here I start with a sequence of numbers indexed by S. And for this sequence T, I consider the random variable x sub t. This is the sum of those of the T sub I for which I belongs to Y. So again, I think of Y is the random subset of S. So that simply means that in the sum here, for each term I flip a coin and I take the term in the sum if the coin comes head up, which has a probability P. So that gives a random variable, and what I would really love to be able to do is I give you a family of sequences, and I would like to compute the supremum of these random variables as a function of the geometry of the family T. Now, what does it mean as a function of the geometry of the family T? Well, that's part of the problem, what it means. In which sense do you have to think of that? That would be very nice if one could do that. Now, when you start thinking about this problem, then you realize that you are not going to be able to do any progress on that before you solve some other problems. And one of them, I want to mention it, which is the following. Now, here, given again a family of sequences indexed by S, I would like to compute the supremum over this sequence of the random variables, which are the sum as follows. They are the sum of epsilon I t sub I. Now epsilon I are just random plus 1 or minus 1s. So I would like to be able to solve that as a function of the geometry of T. Now, here, to study these quantities, the observation is that there are two obvious ways to bound such a process. One way is you put absolute value around. When you put absolute value around, you put the absolute value inside. So epsilon I has absolute value 1. So you get a bound by the supremum of a T of the sum of the absolute value of T sub I. That's one bound. Now, a second bound you can study if you know a little bit about probability in Banach space. If instead of putting the epsilon I here, you put independent Gaussian, then you get a quantity which is larger by, it's a comparison theorem. It's really easy to do that. You get a larger bound. And when you put Gaussian instead of putting random sign, as I explained before, you completely understand the situation. So you have these two different bounds, but you also have mixtures of them in the sense that I explained. And I call the problem of knowing that if really the mixture of these two bounds is really the only obstruction for this quantity to be large, is called that the Bernoulli problem, and this one at a little bit larger price because I have spent, I don't want to know how many years I have spent studying that. And I think it's a nice problem also. So, when you realize that, you say, okay, it's a nice problem, but it's clear I won't solve it. So, does it mean that I completely have to give up on these processes? Well, okay, this program here of trying to understand the understanding the supremum of the selector process of I'm not going to be able to complete it in this generation. So what do I do? Still, can I get anything at all? Okay, then I can try to remember what I said about Gaussian processes and try to get something. So since I cannot fulfill the program I would like, I will try to find a less ambitious program. Now, less ambitious program would be, okay, let us make matters simpler by considering only sequences which are non-negative. And now let us look at the set where the supremum of the process is exceptionally large, more than 100 times the expectation. Now, could it happen that this set is very small in some sense, just like it was for Gaussian processes? Now, Gaussian processes, I explained to you that the set where the Gaussian process is exceptionally large is small in a sense that is contained in the union of half plane with half spaces with the sum of their measure at most 1/2. So maybe here I could have the same. So really the problem then you come up with is maybe it would be natural to expect that this exceptional set where the Gaussian process, where the selector process is much larger than its expectation, is p-small in the sense that I explained, which means it's covered by a family of set H sub I for which the sum of their measure is less than 1/2. This set playing the same role as the half spaces for the Gaussian processes. So it would be natural to expect that. Now, when you think about that problem, then you realize that this is not the natural problem to ask. You try to find what's the abstract structure underneath that. And if you think that really if you think 1 minute, you realize that this would be true if the main conjecture is true. And somehow the main conjecture is the more fundamental fact that should be studied. But that's one motivation for studying the main conjecture. Okay, now that ends the second part of the talk. Now, in the third part of the talk, I'm going to discuss the main conjecture itself, but the organizer made clear that they would not refund my plane ticket unless I give you a 5-minute coffee break now.
Refunding your 5 minutes so you can exceed the clock bound.
Actually, I'll be. Okay, maybe I'll go slower.
I have a question that's off this topic, but it might be something you know
Yes.
about. So you have this. Hey, good to see you.
Enjoy your thoughts. I'll come to the second part also.
You and Sarek have this old theorem about isomorphic version of the Zawar-Shalach.
Oh, I complete. Yes.
If you have a subset of 0, 1 to the n of large cardinality, then if you project onto some fraction of the coordinates, the convex hull contains a large box.
Yes. Yeah, I completely forgot about that. What I remember is that it took such a long time. These sequences of 0 and 1, these are the curse of my life. Because I cannot help finding that these are the most essential problems there, and they are just so terribly difficult. Yes.
Okay. That's bad news for me to ask you my question.
No, I completely forget. It's too long. It's really too long. I won't remember.
I'm interested in the following situation. I have a subset of the unit cube.
Yes.
Actually, let me make it the L infinity unit ball instead. Just for the question is simpler to state if it's the -1 to the n. My subset is not a subset of the corners. It could contain interior points. But it has the property that it's a good covering code. So in other words, if I put L1 balls of radius 1 minus epsilon times n around these points, then they cover the entire cube. Alright, so, if I said L1 ball of radius n, then my set could just consist of the origin, and it already contains the entire cube. Instead, you need to have a points because I'm trying to cover with L1 balls that are a little bit too small to hit the corners. Okay. I want to that if I project onto a coordinate subspace consisting of many coordinates, then I get a box, an L infinity ball of radius epsilon is contained in the convex hull of the projection. So compared with your Sarek paper, I'm replacing the cardinality hypothesis with a L1 covering hypothesis. And I want to get a similar conclusion that the projection onto a constant fraction of the coordinates contains a big L infinity convex hull.
I smile because you start by saying, I take these balls of radius 1 minus epsilon, and then you say, oh, but already when you say that, there was this amount of difficulty already in the previous sentence. Overwhelming.
So I only quote the end, but it sounds a little bit like this Borsuk conjecture situation, but then you're doing a projection, so you're throwing me.
The Borsuk conjecture.
Or this thing that Jeff Kahn and Gil Kaleidis. But then you're doing a projection, so it's a different world what you're talking about.
So the Borsuk conjecture, I have like a subset of the sphere, so that every point is within.
Also, it's the same metric. You're switching between L infinity and L1 here, so I'm not.
You just need to be aware that you're wearing the microphone still.
The gist of the argument was clear. So there's this tiny star, you have lots of curves. You have several chemistries. So sort of now you can sort the intervals for each pyramid when they have these like bars that you fill. There's some tiny star which sort of cuts through all of this. Now within each interval there is some point within the interval J, there is some point in J that have R pebbles, right? So now from all these constants, and now you have either so half of them like occur before this time t star, cutting through, or half of the bottlenecks occur after. Now if like half of the bottlenecks, at least half occur before, then you look at the last bottleneck before t star. Then you have R pebbles there, but all the other bottlenecks that you already took care of, they still contain at least one pebble because t star is like cutting all of these pieces, right? So then you have to just by fitting the confidence basically. And there are at least the S guys that contain one. And the other, okay, but maybe like T star came early and there are a lot of points after. Oh, but then you look at the first max point occurring after since it is the first point, yeah, that's by assumption because you know they're all finishing. Like you know that for each pyramid, you know the following 14 tablets. You start tabbling in. So it's one of two scenarios for each pyramid. So scenario one, start tabbling in, you reach max, now this time T star happens, and then you pull up. Or the other way around happens instead. Start tabbling, you reach T star, now you reach the max. And it's a case analysis provided on what sort of whether your bottlenecks come before or after. I don't know, maybe you have to adjust for the package or something, but you know, that's the idea. And together you're about your space bound for the whole public country. And so now you know that so we can solve the pyramids. We can do one yeah, so now once you have
Very nice.
Yes, that would be wonderful. I mean, if a big problem in the world is that there are no intermediaries.
So I'll give people 2 more minutes to get back in.
Okay. Okay. So now in the last part of the talk, I'm going to discuss the main conjecture itself. As you observe, the main conjecture deals with very basic object. We don't have much data, and what do we do? Now, as I started as an analyst, now when I see a problem I cannot solve, I try to use the Hahn-Banach theorem. So by doing that, then you get the following idea. Given a number delta, let us say that a probability measure nu on 0, 1 to the s is delta spread, if it has the following property. Well, the new measure of a set h sub I, now I remind you that h sub I means that these are the subset of S that contain I. The measure of h sub I is less than delta to the cardinality of I. And the idea of that definition is that if nu is delta spread for small delta, then the support of nu is large in some sense. The word is spread all over. Now, when I use probability measures here, you understand that there is no measure theory. I'm on a finite set, so this is simply a system of weights. Now, example of mu p itself is p spread, because mu p of h sub I is p to the cardinality of I. Now that's sort of misleading. Here is probably what's the most important example. If you consider, recall that the n is the cardinality of S. So consider the measure that is uniform on the sets of cardinality 1. So for each set of cardinality 1, nu gives weight 1 over n. Then this measure is 1 over n spread. Why? Well, then I have to compute nu of h sub I. Now, if cardinality of I is bigger than 2, then I is not contained in any set of cardinality 1. So nu of h sub I is 0. And if I has cardinality 1, then nu of h sub 1 is 1 over n. Okay, so that makes it obvious that nu is 1 over n spread. And somehow this is the fundamental example. Now, here is a definition. One problem I'm trying to solve here is so difficult to work with p small sets. How do you prove that a set is p small or is not p small? Especially, how do you prove that a set is not p small? Okay, so I'm defining another notion here. Now, given delta, a class is called weakly delta small if it does not carry a delta spread probability measure. Now, this is complicated, getting complicated. Now, you have to think a delta spread probability measure is something that takes a lot of space. It needs a lot of space to live in. So if I do not carry such a thing which takes space, means I'm small, right? So a class is weakly delta small if it does not carry a delta spread probability measure. And what's the use of that is trivial fact, as the terminology indicates that if
what does it mean that it does not carry?
It does not. It does not support. It won't support. I cannot find the weight on the sets.
Oh, I see.
So, if a class A is p small, then it is weakly p small. Now, the way I give. Now, proof of that. Now, that will help us to understand what it is. Okay, so I I go by contradiction. I say assume for contradiction that A is not weakly P-small. So by definition, it means if it's not weakly P-small, it carries a P-spread probability measure nu. Now, on the other hand, assume that A is contained in the union of a certain H sub I. Okay, then A carries nu, so it means nu of A is equal to 1. So nu of A is equal to 1. Okay, here here it's obviously nu. A is contained in the union. A is contained in the union of H sub I, so nu of A is less than the sum of the nu of H sub I, and since nu is P spread, then by definition it means that nu of H sub I is less than P to the cardinality of I. So 1 is less than the sum of the P to the cardinality of I. So whenever A is contained in a union of H sub I, then the sum of the P to the cardinality sub I is bigger than 1. It can never be less than 1/2. So A is not P-small. So it shows that if A is not weakly P-small, then A is not P-small. Now, as I explained, when the smaller P, the more P-small sets they are, and the smaller P, the more weakly P-small sets they are. And somehow I believe that the notion of P-small and weakly P-small is the same in the following sense. I believe that there exists a universal constant, so that if you take any weakly P-small set, then it is P over 100 small. So provided you accept to change by a constant factor the value of P, then the notion of P-small and weakly P-small is the same. Now, actually, I spend also a lot of time on that problem, and this problem doesn't deal with the structure of up and down classes, but it doesn't appear to be so easy either. So let me give you more examples of delta spread measure. So if the measure nu is uniform on the subset of S of cardinality K, so each set of cardinality K, it gives the same measure, then it is K over N spread. It's an extension of what I said when nu is uniform on the subset of cardinality 1, then it's 1 over N spread. And there are nice operations you can make. You can have a stability by tensor product. That simply means that if your basic set S is the disjoint union of R blocks, and if on each block you consider a delta spread probability, then when you make the product, so the set 0, 1 to the S, you can consider it as the product of 0, 1 to the S1 times 0, 1 to the SR. Then on this one, you consider the product measure. Okay, then this one is delta spread. It's absolutely obvious to check from the definition. But somehow it's interesting that sometimes you combine two trivial observations and then you get something non-trivial. It's not transitive. Triviality is not transitive. You see? You see. And so if you combine this example here with K equal 1 and we make a tensor product, then you get something very interesting, which I didn't discover, by the way. It was well-known example Noga alone explained to me. So suppose your basic set is the union of R blocks. Each block has a cardinality M. Now consider the class of sets which meet each block in exactly one element. Now you look at the uniform probability on that, and then you check that it's in fact a tensor product. So you check that it is 1 over M spread. Also, you see that the uniform probability nu is supported by A0, but it's also supported by the class of sets which meet each block in at least one point. Here I was meeting in 1 point, it meets at least 1 point. So this is, I have this up class A here. So this up class A, it carries a 1/m spread measure. So by definition, it is not weakly 1/m small. So it is not 1/m small. And if I compute the measure mu p of A, okay, I found that this is, okay, I compute, this is obvious. But if I take R large, if I fix M and take R large, this can be arbitrarily small. So with this construction, that provides an example of a set A for that mu p of A is as small as I wish, but A is not 1/m small. So you give me M, then I provide you with a set which is not 1/m small, but which is mu p of A is as small as you want. That's a statement that I explained at the beginning of the talk, that being p small and having a small measure for mu p, these are very different statements. So I simply here I rewrite the basic definition for class A. AQ are the set that cannot be covered by Q sets in A. Now, weak form of the main conjecture, if Q is large enough and mu P of A is close to 1, then AQ is weakly P small. Now, AQ meaning weakly P small is weaker than saying AQ is P small, so this is a weak form of the main conjecture, but it would be very interesting to prove that. Now, one remark I can make in passing, say here I could ask weakly P over 10 small or weakly 10 P small. That's all the same. These are all the same, these conjectures are all equivalent, provided, of course, I take different values of P. So there is a certain robustness in that.
Was the robustness there in the strong conjecture?
Okay, it's difficult to explain, but the fact, actually, when I prove that the main conjecture is true for the set B, which is the Hamming ball, there is a huge lot of room there, you see. So I believe these things are all very robust, somehow. Now, let us try to think how, let us say, okay, this, you know, you come back to your hotel and you say, I saw these talks, this is outrageous, this guy is crazy, these conjectures, this cannot be true, let me find a counterexample. Okay, so let me find a counterexample. Now, find a counterexample, okay, you must find a set A, which is measure close to 1, and you must find a P-spread measure, which is carried by AQ. So you must find this measure. There's no way. Okay, so you don't know whether you have to start to look for A or look for the measure, but in any case, at some point you'll have to come up with the measure. So let us face, what do we take for the measure? Well, okay, we say probably it's not going to be a big loss if we say that the measure is carried by set that all have the same cardinality. So let us make that act of faith. Okay, it's not going to be. Then I have to construct a set A. The difficult part is I have to construct a set A so that B is contained in AQ, which means I have to find a condition on A so that whenever I take a set in B, it cannot be covered by Q elements in A. That's the hard part. I have to enforce that. Now, the most natural way to do that is to say, okay, A will consist of sets that will meet the set in B in less than the proportion Q of their cardinality. So the cardinality of the J has a cardinality M, so I will take I having intersecting G by a cardinality less than M over Q. So then if I take Q sets in A, I can never cover J with that. That's a natural way to do. But the problem is that will never work. That I can prove that. I can prove that whenever you do this construction, the set A has an extremely small measure. So this obvious way to make a counterexample doesn't work. And so actually, so in the paper, it's stated as a theorem, which actually goes a little bit beyond that, and which is one of the main support of the main conjecture, is that the obvious approach to a counterexample is not going to work. Okay, it's a non-trivial fact. Now, okay. Now you say, okay, maybe the reason I cannot make progress on that is I don't understand this operation of taking the union of Q sets. It really bothers me. So I'll try to find a definition that gets rid of that. Now let me explain to you what I have thought of. Now the definition. Consider a down class A and a subset I of S, and I define another down class A sub I. These are simply the subset of I that belongs to A. Or if you want, that's the same, the intersection of I with a set in A. So now it's a down class, but it's contained in 0, 1 to the I. Okay, and you make trivial observation. If the set I belongs to A, if and only if the class A sub I is the whole of 0, 1 to the I. Okay, that's obvious, because if I belongs to A, then I belongs to A sub I, and since A sub I is a down class, then it contains a set, it contains everything underneath. Now, let us fix a number alpha. Now, you have to think that alpha, this is 1 over 100. Huh? This is a number. Now, you consider the measure mu alpha on 0, 1 to the I. That's the same as the measure mu p. That's a product measure that gives weight alpha to 1 and weight 1 over alpha to 0. And you think to the quantity mu alpha of A sub I as a function of I. That's getting complicated, but I'm going to make a picture. Next slide. Now, so as a function of I. So this quantity decreases when I increases. And moreover, if I belongs to A, then mu alpha of A sub I is 1, because A sub I is a whole 0, 1 to the I. So the idea is to think of the set where mu alpha of A sub I is strictly less than mu p of A as a set of points which are far from A. So here is the picture. Here is the whole of 0, 1 to the S. Here is my down class A. So I take a subset of S. I look what is underneath here. So I intersect with A. This is the way you have to picture the class A sub I. And now I have the measure mu alpha which lives on that cone here. And I look at mu alpha of A sub I. So somehow the proportion of that cone, the proportion for the measure mu alpha, the proportion of what proportion of that cone is A sub I. So when I belongs to A, proportion is 1, but when I get far, proportion becomes small. So the point where the proportion is less than mu p of A, in some sense, they are far. That's a nice way to consider. So here is the conjecture. There exists a universal constant alpha, so alpha equals 100, which has the property that for each down class A, then the set of I where mu alpha of I is less than mu p of A is p small. Now this conjecture is stronger than the main conjecture. Now the whole proof is contained in the rest of the page, but since I'm running a little bit late, I am not going to give the proof, the whole proof. It's really a 5-line proof. Okay, just to give part of it, the main observation is it's a nice elementary fact. Now, if I give you alpha, so alpha equals 100, there exists a number q which has the following property. If you take a set A with mu alpha of A bigger than 1 minus 1 over q, then AQ is empty set. You can cover everything with Q elements of A. Now that's a statement where alpha equal 1/2. We all know that if you take the measure that gives same weight to 0 and 1, and you take a set of measure 1/2, then you can find in it a set and its complement. So the union of the two will be the all index set. Okay. Now I want to keep my time to discuss, so I rewrite here the conjecture one. There exists an alpha such that for each down class, the set of I where mu alpha of A sub I less than mu P of alpha is P small. Now here is the conjecture, a stronger version of that conjecture, which looks much nicer somehow. It says, now I don't believe they are well, I believe they are all true, but they are not formally equivalent. There exists a number alpha so that whenever I take a down class and a p-spread measure, I have the following inequality. Now that's a very beautiful inequality. Here on the left hand, I simply have the measure of the set. Now on the right hand, I have a product of measures of set and sets. Now they have powers. Now I recall that nu is a probability. So the sum of these exponents here over all the choice of I is equal to 1. Huh? Now each of the terms here measures somehow the size of a projection of A. So I project A to get the set A sub I, and I measure the size with the set with mu alpha. So that's typically going to be a number very much closer to 1 than mu P of alpha. But I take the product of many such quantities, a great many such quantities. And the point here of the measure being nu spread is that I take this projection involved a lot of different directions. Now, why conjecture 2 is implies conjecture 1? Well, when I have this inequality here in the product, here the term that involved in the product, they cannot all be smaller than mu P of A, simply. Well, some have to be larger because I take a product, I recall that the sum of the powers is equal to 1. So if the measure nu was supported by the set where mu P of A sub I is less than mu P of A, okay, then the right-hand side would be less than mu P of A, which it cannot be. So that means I cannot find nu supported by that set, and if I recall the definition, it exactly means that this set is P small, it cannot carry a P-spread measure. Now, so I believe this inequality is true. Now, if you want to disprove this inequality, you have to find both A and nu. And the difficulty is that I can prove that A and nu would have to be very complicated to disprove this inequality, in the sense that if you construct nu and A from simple P's by iterating simple operations, you are never going to reach a counterexample that way. For example, I can prove that this inequality is true when nu is uniform of the subset of a given cardinality. Now which are, so when formulating this inequality here, you really have two parts in the data. You have a down class and the measure nu. So like here, you can prove statement by varying nu, and you can prove statement by varying A. Now, so you can ask, okay, I would like that this to be true for all down classes, but maybe I can investigate for which down class this is going to be true. And then you realize that if you want to have a chance to prove anything, it's not going to be enough to use this measure mu P that gives a certain weight to 1 and a certain weight to 0. You have to use more product measures. So to study the down class that satisfy the inequality star, you have to use more product measures. So let me introduce this product measure. These are simply the product measure on 0, 1 to the s that gives an arbitrary weight to 0 and an arbitrary weight to 1. But I found that it was interesting to renormalize them in a certain way. So the basic parameter is the sequence t sub I, which will decide what is the weight of 1 and the weight of 0 at the point I. So lambda sub t is the product measure, and then the factor I, it gives weight. The weight of 1 is 1 minus exponential minus t sub I, and the weight of 0 is exponential minus t sub I. Now, why that normalization? I'll explain in a moment why that. And now the idea is you would like to really understand as a function of t how looks this quantity minus log of lambda t of a. Now the minus log is just a kind of normalization. So you given a down class, you try to understand what is its measure for a product measure with arbitrary weight. Okay, so trivial example of that is when A consists only on the empty set. Now, if it consists of the empty set, then lambda t of A is, well, it's a product of the weight of zeros. So when you take minus the log, you get the sum of the t sub I. That's, in that case, it's a very simple function. Unfortunately, that's the, yeah. That's the only case. So the idea here is like the Hahn-Banach theorem. You would like for a down class to understand the measure lambda t of A. So you'd like to understand that the function of t, what is minus log of lambda t of A. Now that's going to be a complicated function. So since, okay, the way to study a complicated function is to compare it usefully with a simple one. And the simple function I found are very useful. I call them polynomials. They are simply functions. They are a sum of terms. Now, each term is a constant times a product over a certain set of the t sub I. T indexed by the set I is a product of the t sub I for I in capital I. Okay, so it's a kind of monomial, and I look at linear combination of that with positive coefficient. So this is a much simpler function than let me define the following. Let me make the following definition. Given a number gamma, positive, now a down class has the property C gamma if the following occurs. Whenever you give me a specific point here, I can find a polynomial depending on that specific point, which has the property. Now, everywhere the function minus log of lambda t of A is bounded by the polynomial. But at the specific point that you gave me, this inequality can almost be reversed. Well, almost be reversed is, there is this little gamma that comes in here. But basically, it can be reversed. So you have to make the picture like that. You have this complicated function here, and then you, given a specific point, you approximate, you find this simple function that is above the complicated one, but at your specific point, basically, it is the same. So it's really the idea of the Hahn-Banach theorem. The Hahn-Banach theorem, you have these convex functions, and they are complicated, and you approximate them by linear function, and at a given point, you can have them touch. Now, here there is a theorem. Actually, it's a sort of a shame to call that a theorem because it is, as I said, I cannot prove anything. So everything I call theorem is in fact very easy. Now, suppose you have numbers gamma, delta, and alpha, which have the following relation. Alpha is less or equal than 1 minus 1 minus p, this is complicated, gamma over delta. Now, it says that if A is a down class with property C gamma, and if nu is delta spread, then I have this inequality. Now, that's inequality I would like to prove everywhere when for delta equal p and any down class. Now here in this theorem, I'm not doing that. I'm saying for a down class which has property C gamma. Now that's really the difficult part. Which are the down classes which have property C gamma? Huh? But still, I can prove there are few down classes that have property C gamma. So it's not completely empty. So example here. Now, suppose I take delta equal p, because this version of the inequality I had before, I wanted delta to be p spread. So if I take delta equal p, I see here the relation is satisfied for alpha depending only on gamma. So for example, if I could show that all down classes have property C gamma for gamma equal 110, then I would prove that this inequality is always true when nu is p spread, which would basically solve my main problems. Okay? Now, there is, among this choice of parameters, there is another choice of parameter, which maybe I will not discuss in detail. Instead, I want to talk of something related, which is the Kahn-Kalai conjecture. Now, that's a very, very beautiful conjecture. It says, the conjecture that if I have an up class, now, unfortunately, this is not dimension independent. If there is an up class, and if I take delta, well, p over log n is the cardinality of S. Huh? So whenever mu p of A is less than 1/2, then A is delta small. That's what they conjecture. Now, the reason they thought about that is to study the threshold problem. Now, you consider an up class, for example, a class of graphs, and you are asking when the Erdős-Rényi random graph belongs to, for which value of p the Erdős-Rényi random graph belongs to that class. So you are given a class and you want to find the maximum value of p for which mu p of A is, say, less than 1/2. And the Kahn-Kalai conjecture would tell you that, well, to compute this threshold, you have no other way. Within the log n factor, you would have to find for which value of delta A is delta small. And basically, this value of delta, that would be the threshold you are looking for. So it doesn't say that's a practical way to do it. It says, again, that, well, there is no point to try to do anything else. And the version here of the previous theorem, the case that I didn't go through, the second case, shows actually that when A is an up class and the complement of A satisfies the property C gamma, then if I take delta equal gamma p over 10 log n, then when mu p is less than 1/2, A is weakly delta small. Now, how does it compare with the Kahn-Kalai conjecture? Here you have delta equal p over constant times n. Here I have delta equal gamma p over 10 log n. That's the same dependence here, 10 log n, except that I have the gamma here. So of course, that to be interesting, I have to apply that to sets which have the property C gamma, which is where the difficulty is. Now, I could prove something about There exists a gamma. Actually, after I gave this lecture in Paris, somebody looked at the paper and said, we can prove it with gamma equal 1. So the following two classes have property C1. First, the empty set. Now, this one I explained why, because minus log of lambda t of A is T1 plus T2. That's already a polynomial, so I don't need to do anything about it. But there is another case which is not trivial, which is the class which consists of all the sets except S itself. Also has property C1. Now, you're going to tell me, okay, that's a little bit ridiculous to have only these two. But the way the property C gamma is designed is that it has wonderful stability properties. So let me explain these stability properties. Now, suppose your space S is a union of blocks. Now, on each block, I'm given an up class. And now I construct a new up class in the following way. I take a set and I intersect with each of the block. Now, for each of the block, I look whether it's in the corresponding up class or not. If it's a corresponding up class, I put a 1. If it's not in the corresponding up class, I put a 0. Then I get a sequence of 0 and 1, which is sequence of length r, the same number of blocks. Now, I have a last up class. And if this sequence belongs to this last up class, then I decide that my original set belongs to the new subclass here, and otherwise it doesn't. So I have an up class for each block plus an extra subclass A0, and then I construct a so it's the kind of operation like taking union on blocks and disjoint union and intersection on blocks. Now, this operation here is the property C gamma is stable for that interaction. If all the up classes are used by making this construction have property C gamma, the resulting class has also property C gamma. So even though here I start with only these two trivial examples, when I iterate that many times, I get quite a few sets that have property C gamma. C1 actually. So for this set here, the previous theorem is not empty. Now, of course, so what this means is I will not be able to find a counterexample to my inequalities by iterating simple operations, because what I said is exactly that, is when I start with something simple and I iterate this simple operation, inequality is still true. So to find a counterexample, I have to find it complicated in one time, okay? Now, of course, the true problem is that there exists a number gamma so that every down class has property C gamma. Now, that looks just, it cannot be true. Well, it cannot be true, but if it is true, this would completely transform our understanding of the combinatorics of finite sequences. That's what I really. Now, I'm not offering the price. I'm just suggesting that's a difficult problem, and that would be probably the correct amount for a positive answer. Now, of course, if it's a negative answer, it's less interesting, but in the paper, there is a chain of conjecture. Here I gave only 3, but there are maybe 10 conjectures of increasing difficulty. If you can destroy the last one, at least you see a little bit clearer, because maybe you can destroy a little bit further. Okay, thank you very much.
Time for a couple questions before we take a break.
You have a price for the negative answer?
Oops, I shouldn't have touched that. Sorry, I'm completely deaf. So what was the question?
If you have a price for the negative answer?
For the negative answer, for the main conjecture, there is a price. Either is a southern line, either positive or negative. For the negative, now if you solve any of the stronger conjecture, of course, the negative answer for the stronger conjecture, there is no price. I didn't try long enough. Yeah. Now, okay, another thing is, you see, this is a problem for people who can manipulate the software to understand. You have to understand how to start to study this property C gamma. So you have to start with some concrete simple sets and then make graphs of the function and try to picture something, you see, which is not something I know how to do. So maybe when you do that, it's obviously wrong.